Hey, hello everybody. Today we're going to be talking about antiderivatives. Antiderivatives. We've learned about derivatives. Now we're going to be talking about antiderivatives. So if you know what the prefix anti means, how does that relate to our derivatives? Well, we're going to find out right now. We'll play a little Jeopardy. If you know the game of Jeopardy, I'm going to give you the answer, and you are going to give me the question. So think about that. I'm going to give you the answer, and you are going to give me the question. And I don't want all of this stuff up there right now, so I am going to do this. So give me a function that has the following derivative. So the answer is the derivative. You're giving me the question. I give you the derivative. You give me the question. So think about it for a moment. If you need to pause the video to think about it and then come back, please do so. But here is the derivative of a function. What function has this derivative? Well, if you said this, x cubed, you would be correct. Because x cubed, if you take the derivative of x cubed, it's 3. Coefficient comes down, subtract 1 from the exponent, you get 3x squared. So now you're going to do that for each one of these. So again, think about it for a second. Pause the video while you think about it. And then come up with the function, the question to this answer. If you came up with 4x to the 5th, you would be correct. If I took the derivative of this, you would get this. Next one. Again, take a moment, pause it, think about it. I'm just going to supply the answer for you, that this is going to be the square root of x, which is also equal to x to the 1/2. So when I take the derivative of it, I end up with that. And the last one, 4x, 4/3 x to the 1/3. What function has that derivative? Well, if you said x to the 4/3, you would be correct. Because you would take that, multiply it by the coefficient here, then subtract 1 from this exponent, which will give you the 1/3. So again, little Jeopardy, I gave you the answer, you gave me the question. What's this have to do with antiderivatives? We'll find out, Oh, constant? What does that mean, constant? Look at the pretty clouds, and it's in there, constant. Let's go back. Let's eliminate this, I don't like this. Constant, what do you mean by constant? What do we know when we take the derivative of a constant? It goes to 0. So that means, what if I added a constant to this? Any constant. It could be 5, it could be pi, it could be 11. If I took the derivative of this function, would I still get 3x squared? I would, because when I take the derivative of x cubed, it becomes 3x squared. When I take the derivative of a constant, it goes to 0. So that means each one of these could have any constant added to this. Any constant. Again, it could be 5. We could have plus 5 right there. We'd still have that same derivative. This could be plus negative pi. It would still have the same derivative. This one, doesn't matter. Any constant. 4.7. 85. When we take the derivative, since they're constants, they go to 0. So that's something that we have to keep in mind, and that's why that was there to remind me to talk about the constant. Here's a theorem. Look at that on the nice blackboard. The representation of antiderivatives. If f is an antiderivative of little f, I should say big F. If big F here is an antiderivative of little f on an interval I, then big G is an antiderivative of f on the interval I if and only if big G is in the form. What? Big G of x equals big F of x plus c for all x in I where c is a constant. What does that mean? It sounds more complicated than it actually is, but just think about what we just did. You just did this. This is the antiderivative of this. Since this was this guy over here, f prime of x, 3x squared is the derivative of x cubed plus 5. This is, if you want to call it this big G of x equals big F of x plus c. So that's all that theorem is talking about. It's just saying that what we just found in that Jeopardy game is the antiderivative. That's all that theorem is saying. So don't fret. I know there's a lot of words there, but that's all it's saying. Uh-oh. F of x equals 2x. What does g of x equal? Big G of x. So basically, what is the antiderivative of 2x? Antiderivative of 2x. So that means a function whose derivative is 2x. I think we could all figure out that it's x squared. But we can't forget our plus c. Why that plus c? Well, remember what a derivative is. The derivative is what? Right? And if you would have said the slope of a tangent line at a point on the curve, you would be correct. So this means that this could have any shape. So I'm just going to draw a parabola on here of x squared. So there's x squared. There's x squared. And the slope of any tangent line along there at any point would be 2x, the equation 2x. But that plus c, in this case, c is what? 0. But what if I moved it and put the parabola down here? Should be the exact same shape as the green one. So now the parabola is shifted down. So my c is different, but would the slope of those tangent lines along that curve be any different? They shouldn't be. They should be exactly the same and represented by 2x. That is true if I shifted the parabola up. Our c now is a positive value going up, but the slopes of the tangent lines do not change. So think about the slopes of the tangent lines would still be 2x regardless of where I am. So if I were to draw a tangent line on this curve, the slope of it at the exact same point should be exactly the same, and it should be exactly the same at the exact same point. That's all we're saying when we take the antiderivative and we find that c value, which we'll learn eventually. Right now we just do plus c. Where did this all come from? Well, it all came from an idea of talking about the derivative and trying to turn this, the derivative of dy dx is equal to f of x. Well, I need to find what function has a derivative of f of x. And the way that it came about is they multiply both sides by dx. So we're left with dy equals f of x dx. But I needed to get rid of the d part of the dy, and they needed just y. So what they did is they came up with, and we'll talk in more detail later, they came up with an integral or an antiderivative. And it looks like that. It's a funny little S looking shape, and we'll talk about where that comes later. There you go. So you take the antiderivative of both sides of the equation, because whatever you do to one, you do to the other to keep the equivalence of it. This then becomes, when I take the antiderivative of dy, you get just y equals the antiderivative of f of x dx. This is known as antidifferentiation or indefinite integration. This symbol and what we do to this function. So you can think of f of x as the derivative and y as the antiderivative of that function. So the basic integration rules are what we're going to talk about. The antiderivative of big F prime of x dx equals just big F of x plus c. So when we take the antiderivative of a function, if you think about the antiderivative of the derivative, we get this function f of x. I know this is a tough concept because I'm using a lot of words, but just think about what we did with a function to find its derivative, and now we're going backwards. We're taking the inverse operation. So we took a function, we took the derivative to come over here. Now we're just going to be stuck with this function, and we're going to take the antiderivative to get back to that original function. Alright? And remember that inverse nature. It's like multiplication and division. You multiply x by 5. In order to undo that, you divide that by 5. Derivative, antiderivative. Let's play with some basic integration rules, okay? Actually, that's going to be the next part of the video. So tune back in for antiderivatives part 2 to find out how we use some of these basic integration rules, kind of like our basic derivative rules. All right, so tune in again. Hope you enjoyed this. Johnstone out.